Okay, so at the previous lecture, we introduced the maximal spectrum and the Confined transform for commutative unital Banach algebras. So let's briefly recall the main points of the construction. Suppose that A is a commutative unital Banach algebra. So we consider the following two sets. The first set is the maximal spectrum. It is denoted like this. And it is the set of all maximal ideals of A. And the second set is the so-called character space. It is denoted by A hat. This is the set of all non-zero characters of A. That is, of all non-zero homomorphisms from A to the complex numbers. So we have an obvious map from the character space to the maximal spectrum, which takes each character to its kernel. And we proved that for each commutative unital Banach algebra, this map is a bijection. So we will often identify the maximal spectrum with the character space. Also, let's recall that all maximal ideals of such an algebra are automatically closed, and all characters are continuous. Okay, now we topologize the maximal spectrum in the following way. So all characters are continuous. So A hat is a subset in the dual of A star. We equip A star with a weak star topology. And so we get the induced topology on A hat, or equivalently on the maximal spectrum. And this topology is called the Confined topology on the maximal spectrum. We proved that the maximal spectrum becomes a compact Hausdorff topological space. Basically, this is an easy corollary of the Banach hollow glue theorem. So A hat is contained in the closed unit ball of A star, and the closed unit ball is a weak star compact. So, and it's very easy to show that A hat is closed in the unit ball. So it is compact because it is a closed subset of a compact space. Well, now the Confined transform of A is an algebra homomorphism from A to the algebra of continuous functions on the maximal spectrum. This homomorphism is defined as follows. It takes each element of our algebra to the function A hat, which is called the Confined transform of our element. And A hat is given by the following simple formula. If K is a character of A, then by definition, A hat is given by this formula. So this is the Confined transform. Well, the Confined transform is a unital algebra homomorphism. It is bounded, and its norm is less than or equal to 1. Actually, it is exactly 1 because it is unital. It has some remarkable properties. In particular, it is spectrum preserving. And the kernel of this homomorphism is the so-called Jacobson radical. That is the intersection of all maximal ideals of A. So if A is Jacobson semi-simple, which means that the Jacobson radical is trivial, we see that A is algebraically isomorphic to a subalgebra of the algebra of continuous functions on the spectrum. It is algebraically isomorphic, but of course it is not necessarily topologically isomorphic. So the Confined transform, even if it is injective, if A is Jacobson semi-simple, then gamma is injective, but it is not necessarily topologically injective. So we will see some examples at which this homomorphism is not topologically injective. Okay, so today let's first of all let's discuss some important examples. In all our examples, we will deal with some subalgebras of COX, where COX is the algebra of continuous functions on a compact Hausdorff topological space. So in particular, we will see that if we take the algebra COX of continuous functions on a compact Hausdorff topological space, then roughly the maximal spectrum of this algebra is X itself, and the Confined Transform is just the identity map of COX. This is what we are going to show. Okay, so we suppose that X is a compact Hausdorff topological space. And for each point in the space, we denote by epsilon x the respective evaluation character of COX, which takes each function to f of x. And we denote by mx the kernel of this character, the set of all functions that vanish at x. We have the following lemma. For each proper ideal I in C of x, there exists a point x in our space such that I is contained in the ideal mx. In other words, we can always find a point such that all functions from our ideal vanish at this point. This lemma is a kind of weak Null-Stellensatz for the algebra C of x. Well, okay, let's now try to prove this result. Suppose that this is not the case. So suppose that for each point x in our space, we can find a function fx in our ideal such that this function doesn't vanish at x. Well, fx is continuous, so if it doesn't vanish at x, it doesn't vanish on a suitable neighborhood of x. There is a neighborhood ux of x such that for each y in this neighborhood, fx of y is not 0. Now, well, x is compact, so it is covered by finitely many such neighborhoods. So ux1, uxn by compactness. Let's now define a function f by the following formula. So I claim that this function sits in our ideal I, simply because we can also rewrite this function as follows: fxi complex conjugate fxi. And since big I is an ideal, and each fxi sits in our ideal, we conclude that the sum is also in our ideal. So f belongs to I, but on the other hand, it's immediate from the construction that this function is strictly positive everywhere on our space. So it doesn't vanish. It doesn't vanish, so it is an invertible element of C of x. But a proper ideal can never contain an invertible element. So this implies that I equals C of x, and this is a contradiction. And the contradiction completes the proof. As a corollary, we get an explicit description of all maximal ideals in C of X. So as a corollary, we see that the map epsilon from X to the maximal spectrum of C of X, which takes each point, little x, to the respective maximal ideal, is a bijection. Or equivalently, if we identify the maximal spectrum with the character space, C of X hat, then epsilon takes each point x to the respective evaluation character epsilon x. Well, indeed, the previous lemma obviously implies that this map is surjective. So each maximal ideal is of the form mx, but it is injective by Hurson's lemma, which implies that continuous functions separate the points of x. So epsilon is injective. Okay, so this is the explicit description of the maximal spectrum of the algebra C of X. Now, before we describe the Confined transform, let's introduce some notation. Suppose we have two compact Hausdorff spaces, X and Y. And suppose that F is a continuous map from X to Y. Then F induces a homomorphism F dot from the algebra C of Y to the algebra C of X by the following formula. So here are some simple properties of this map F dot. Well, first of all, clearly F dot is a unital homomorphism. It's a unital algebra homomorphism. And the norm of F dot equals 1. Well, this is clear from the definition. If you take the supremum of phi composed with F, then of course this is less than or equal to the supremum of phi. And since F dot is unital, we conclude that the norm of F dot is exactly 1. Second, if we take the identity map of X, then the induced map is the identity homomorphism of C of X. And finally, if we have two continuous maps, say F from X to Y and G from Y to Z, here where Z is another compact Hausdorff space, then if we take the recomposition, GF, then GF dot equals F dot composed with G dot. This is also clear from the definition. So in fact, these properties imply that what we've just constructed is a contravariant functor. We'll discuss this functor a bit later. At this point, it will be essential for us that the above properties 1, 2, and 3, imply that if F is a homomorphism, then F dot is an isometric isomorphism. Well, it is an isomorphism because of 2 and 3, and since the norm of f dot and of the inverse of f dot is equal to 1, this implies that f dot is isometric. Okay, now we are ready to describe the Confined transform, not only for C of x itself, but also for some sufficiently big subalgebras of C of x. So we have the following theorem. So as before, we suppose that X is a compact Hausdorff topological space. And suppose that A is a subalgebra in C of X such that the function which is identically 1, this is the identity of C of X, belongs to A. So A and C of X have the same identity. And also suppose that A satisfies the following conditions. Condition 1, A is not just a subalgebra, but A is a Banach algebra. With respect to a norm that dominates the supremum norm. In other words, it can be strictly stronger than the supremum norm. A typical example is the algebra of continuously differentiable functions on a closed interval. So its canonical norm is strictly stronger than the supremum norm. And A satisfies this condition 1. Condition 2, A separates the points of X. And condition 3, each character of A is a point evaluation. So for each character of A, there is a point X such that chi equals epsilon X. In this case, I claim that the map from X to the spectrum epsilon from X to A hat, to the character space, which takes each X to the evaluation character, is a homomorphism. So the spectrum can be identified topologically with X. And moreover, the following diagram commutes. And here's the diagram. So our algebra A is included into C of X. So here we have the inclusion map. Also, we have the Confined transform. Gamma A. And finally, since epsilon is a homomorphism, we see that by the previous observation, we see that epsilon dot is an isometric isomorphism between the respective algebras of continuous functions. So it acts from here to here, epsilon dot. So I claim that this diagram commutes. In other words, after we identify X with the maximal spectrum by means of these homomorphism epsilon, the Confined transform gamma becomes just the inclusion map of A into C of X. Okay, now let's try to prove this result. First of all, if we look at conditions 2 and 3, we see that they mean precisely that epsilon is a bijection. 2 and 3 together imply that epsilon is a bijection. Let's show that epsilon is continuous. We observe that epsilon is continuous even only if the compositions of epsilon with all evaluation maps from A hat to the complex numbers are continuous. So for each A in A, the map which takes x to epsilon of x applied to A is continuous. This is essentially one of the basic properties of the weak star topology, which was discussed in the previous lecture. Well, indeed, A hat is contained in A star. A star is equipped with a weak star topology, and the map from an arbitrary topological space to the weak star to the space A star with the weak star topology is continuous, if and only if all such compositions are continuous. But what is epsilon x applied to A? Well, this is nothing but A of x, which is continuous by definition, by assumption. So our algebra big A is contained in C of x. So A is contained in C of x. A is contained in C of x, and this implies that epsilon is continuous. So epsilon is a bijection, is a continuous bijection between compact Hausdorff topological spaces. So it is a homeomorphism. Of course, here we use the compactness assumption. And now finally, to complete the proof, we have to show that this diagram is commutative. This is a straightforward computation. So we take epsilon dot, compose it with gamma, apply it to an arbitrary element little a of our algebra, and then evaluate at little x. So what is this? Well, by definition of epsilon dot, this is gamma of A evaluated at epsilon x. Now, by the definition of the Confined Transform, this is epsilon x applied to A, that is just A of x. So we see that epsilon dot composed with gamma is the inclusion map. And so the diagram commutes. And this completes the proof. Okay, now as a corollary, we see that if A is just C of x, where x is again a compact Hausdorff space, then the Confined Transform is an isometric isomorphism and the inverse map, gamma inverse, is just epsilon dot. Well, indeed, because in this case, in our diagram, the inclusion map is just the identity map. Epsilon dot is an isometric isomorphism, and the diagram is commutative. So this really implies that gamma is the inverse of epsilon dot, And so it is also an isometric isomorphism. Okay. Okay, let's now discuss some simple but useful functorial properties of the Confined transform. Let's consider the following two categories. The first category will be denoted by comp. So the objects of this category are compact Hausdorff spaces, compact Hausdorff topological spaces, and the morphisms are just continuous maps. And the second category will be denoted by cuba. The objects now are commutative unital Banach algebras. And the morphisms are continuous unital homomorphisms of Banach algebras. Okay, so these are our categories. Now let's look at the following two contravariant functors, which act in the opposite directions. The first functor will be denoted by C. It acts from the category of compact spaces to cuba. And it takes each compact Hausdorff space X to C of X, the algebra of continuous functions on X. So this is the action of C on objects. And the action on morphisms looks as follows. If F is a continuous map from X to Y, then the respective homomorphism is just F dot, which was defined before. So it acts from C of Y to C of X, and it acts by the following formula. Okay, so clearly this is a contravariant functor. And the second functor acts in the opposite direction. It will be denoted by max. It acts from cuba to comp. And it takes each commutative unital Banach algebra to its maximal spectrum, equipped with the Gelfand topology. Well, this is the action on objects. And the action on morphisms looks as follows. If phi is a unital homomorphism from A to B, a continuous unital homomorphism from A to B, then the respective map will be denoted by phi star. It acts from the spectrum of B to the spectrum of A by the following formula. So here it will be convenient to identify the points of the maximal spectrum with characters. So it takes each character chi to chi composed with phi. Well, why is it continuous, by the way? It is continuous because let's observe that this map phi star is the restriction of the dual operator phi star from B star to A star. It is just the dual of phi. And this map is known to be weak star continuous. The dual of each bounded linear operator between Banach spaces is weak star continuous. So phi star is indeed continuous. Okay, so we have two contravariant functors which act in the opposite directions. And the following exercise establishes a useful relation between these functors. The exercise is kind of triviality. It is true by the very definition, but it is very useful. Well, first of all, for each compact Hausdorff topological space, we have a canonical homeomorphism between X and the maximal spectrum of C of X. So we know that this is a homeomorphism. But actually, we can say more. If we consider all such homomorphisms for all compact Hausdorff spaces X, then the resulting family of homomorphisms will be a natural isomorphism. A natural isomorphism between the identity functor on the category comp of compact Hausdorff spaces and max composed with C. So the composition of these two functors is naturally isomorphic to the identity functor. Next, part 2. Let's now consider the Confined transform. So for each commutative unital Banach algebra, the Confined transform is a homomorphism from A to C of max of A. And if we consider all such homomorphisms for all commutative unital Banach algebras, then the resulting family will be a natural transformation. From the identity functor on the category cuba to C composed with max. In general, it is not an isomorphism, but it is a natural transformation. Here, the word natural is understood in the sense of category theory. So all the respective diagrams should be commutative. So they are compatible with each other. And finally, part 3, these two transformations are related by the following picture. There is a one-to-one correspondence between the set of all continuous homomorphisms, that is morphisms in the category cuba, from A to C of X, and the set of all continuous maps, that is morphisms in the category comp, from X to max of A. And this correspondence is given explicitly by the following formula. If, say, phi is a homomorphism from A to C of X, then we can do the following. First, we apply epsilon x, which acts from X to the maximal spectrum of C of X. And then we compose it with phi star, which takes the maximal spectrum of C of X to the maximal spectrum of A. And this is the element of the second set here. And conversely, if we start with continuous map from X, continuous map F from X to max of A, then we can do the following. First, we apply the Confined Transform of our algebra A. So it acts from A to the algebra of C of max of A. And if we now compose with F dot, so F dot acts from C of max of A to C of X, we get a homomorphism from A to C of X. So these two maps are the inverses of each other. So this is our one-to-one correspondence. What does that mean from the viewpoint of category theory? For convenience, let's look at the dual category to the category of compact Hausdorff spaces. And if you write this in terms of the dual category, we see that this is second set here is the set of morphisms in the dual category. From max of A to X. And this one-to-one correspondence is natural. So it is a functor in two variables, A and X. In the language of category theory, this means that max and C is an adjoint pair of functors. Max and C is an adjoint pair. So max is the left adjoint of C. So this is the main functorial property of the Confined transform. Informally, it means that in some sense, the Confined transform is the optimal way of mapping A into the algebra of the form C of X. It is optimal in the sense that it has a suitable universal property expressed by this bijection. Okay, our next goal will be to extend the Confined theory, the theory of Confined transform, to the non-unital case, to the case of not necessarily unital commutative Banach algebras. In fact, there are many reasons to consider non-unital Banach algebras. First of all, many algebras which naturally appear in applications are non-unital. For example, the algebra of compact operators on an infinite dimensional Hilbert space, or C-star algebras of non-discrete locally compact groups are non-unital C-star algebras. On the other hand, there are several important constructions, for example, stabilizations and suspensions, which play an important role in K-theory of C-star algebras, and which always produce non-unital algebras. And non-unital algebras also naturally arise in applications to harmonic analysis, to representation theory, and to the quantum group theory. Okay, now before we discuss the non-unital Confined theory, let's look at a simple but useful trick, a trick of making an arbitrary, a non-unital algebra into a unital one. The trick is called unitization. Okay, so suppose that we have an algebra not necessarily unital. And let A plus denote the vector space direct sum of A, and the one-dimensional space spanned by a new element denoted by 1 plus. At this point, this is the vector space direct sum. I don't claim that this is the algebra direct sum. And now we equip a plus with the following multiplication. So we define the multiplication in such a way that the new element will be the identity of a plus. And actually, there is only one way of doing this if we want to keep the original multiplication on A. Well, it's easy to see that this multiplication makes a plus into unital Banach algebra. Into unital algebra. At this point, we don't assume that A is Banach algebra. A is just an algebra, and so A plus becomes a unital algebra. And this algebra is called the unitization way. The unitization has the following simple universal property. So we have the following proposition. Proposition 1, which is actually an exercise for you because it is very easy. So we'll suppose that A is an algebra and B is a unital algebra. If we have an algebra homomorphism phi from A to B, algebra homomorphism, let's extend it to a map from A plus to B. So we define a map phi plus from the unitization of A to B, given by the following formula. So it is, it coincides with phi on A, and it takes the identity of A plus to the identity of B. Then it's immediate to see, to show that phi plus is a unital homomorphism. Is a unital homomorphism. And second, we have a one-to-one correspondence. Between the set of all algebra homomorphisms from A to B and the set of all unital algebra homomorphisms from A plus to B. And this correspondence looks as follows. If phi is an algebra homomorphism from A to B, then we can extend it to A plus as before. So we get a unital homomorphism from A plus to B. And on the other hand, if psi is a unital homomorphism from A plus to B, then we can just restrict it to A. And these two maps are inverses to each other. So we have one-to-one correspondence. And moreover, this correspondence is easily seen to be natural in A and B. So it is, again, an adjunction. So we have the unitization functor, which acts from the category of algebras to the category of unital algebras. And the inclusion functor, or the forgetful functor, from the category of unital algebras to the category of algebras. And this result means that these functors are adjoint to each other. Well, so this is unitization. And in pure algebra, this trick is often considered as a solution of all possible non-unital problems. So, usually algebraically minded people believe that often believe that there is no reason to consider non-unital algebras because we can always adjoin an identity and to work with unital algebra. But in functional analysis, this is not exactly the case. Well, indeed, the unitization is indeed a very useful trick, but it doesn't solve all problems which appear in the non-unital case. Okay, well, one more simple observation for proposition 2, which is also an easy exercise. If A and B are Banach algebras, first of all, if A is a Banach algebra, if A is a Banach algebra, then the unitization is also a Banach algebra. A plus is a Banach algebra with respect to the following norm. The norm of such an element in the unitization is the norm of A plus the absolute value of lambda. And moreover, the above proposition 1 holds if A and B are Banach algebras. And if the above spaces of sets of morphisms are interpreted as sets of continuous morphisms. As a simple corollary, we see that all characters of an arbitrary Banach algebra are automatically continuous. Well, if A is a Banach algebra, then each character of A is automatically continuous, and the norm of chi is less than or equal to 1. Well, indeed, we already know that this is true for unital Banach algebras, and since each character on a non-unital algebra can be extended to a character on its unitization, which is a unital Banach algebra, we conclude that it is continuous and its norm is less than or equal to 1. Now, by using unitizations, we can extend the notion of a spectrum of an element of an algebra to the non-unital case. Oh, sorry, before we do it, let's look at a concrete example of unitization, which is quite useful. Concrete example and an exercise at the same time. Suppose that X is a compact Hausdorff is a locally compact Hausdorff topological space. And let's X plus denote the one-point compactification of X. So let's recall that as a set, X plus is the union of X and a new point, denoted as infinity. And the topology on X plus looks as follows. It consists of all open subsets of X and neighborhoods of infinity, which look as follows. This is X plus minus K, where K is a compact subset of X. So this is the topology on X plus. It's a standard fact that X plus is a compact Hausdorff topological space. And in many cases, it can be described explicitly. So one more fact. Fact 2. If we start with a compact Hausdorff space Y, compact Hausdorff topological space, and if we remove a point from the space, so X will be Y with point removed, then X is locally compact. And the one-point compactification of X is nothing but Y. More exactly, there is a homeomorphism from X plus to Y, which takes each point of X to itself and infinity to Y0. So in other words, if our original space X is obtained in this way, if we can embed X into a compact space by adding only one point, then this bigger space will be exactly the one-point compactification up to a homeomorphism. Okay, now, so what is the exercise? The exercise is to prove the following. If we consider the algebra C0x of continuous and vanishing at infinity functions on our space X, then this is nothing but this space consists of restrictions to X of those continuous functions on the one-point compactification that vanish at infinity. So in other words, a continuous function vanishes at infinity if and only if it vanishes, if and only if it vanishes at infinity, literally, in this sense. And second, there is a topological algebra isomorphism. Between the unitization of C0x and the algebra of continuous functions on X plus. And this isomorphism takes each point in the unitization, which looks as follows. Here f is a continuous function. Well, essentially f plus lambda, where in the right-hand side, we extend f in such a way that it vanishes at infinity. I don't claim that this isomorphism is isometric. In general, this is not the case. But anyway, it is a topological isomorphism of these two algebras. So in some sense, the unitization so in this sense, the unitization of C0x reduces to the one-point compactification of X. Okay, now by using the unitization, we can now extend the notion of a spectrum of an algebra element to the non-unital case. So suppose that A is an algebra, not necessarily unital, and little a is an element of our algebra. Then we define the non-unital spectrum of little a as follows. This is set denoted by sigma prime of a, and by definition this is the spectrum of a considered as an element in the unitization. Well, let's now observe that if A is already unital, then we have two notions of the spectrum, the unital spectrum and the non-unital spectrum. And in the general case, they are different for the following simple reason. So let's observe that A is always a two-sided ideal in its unitization. And this obviously implies that any element in A is not invertible in A+. So each element in A is not invertible in A+. And so as a result, we see that 0 is always contained in the non-unital spectrum. The non-unital spectrum always contains 0. However, if A is already unital, this is the only possible distinction between the spectrum and the non-unital spectrum. Now, this easily follows from the following exercise. Part 1. You have two unital algebras, say A1 and A2. Unital algebras. And let A denote their direct sum. Then for each element little a in this direct sum, so this is an ordered pair, A1 and A2, the spectrum of this element, A, is the union of the spectrum of A1 and the spectrum of A2. Well, this is actually a trivial observation. So everything reduces to the fact that such an ordered pair is invertible if and only if both A1 and A2 are invertible. Second, if we now suppose that A is a unital algebra, so we can look at its unitization. It is also unital. And I claim that there exists a unital algebra isomorphism between the unitization and the direct sum of A plus C. Well, maybe it would be more convenient to write this in the opposite way. From A plus C, the algebra direct sum, to the unitization. And this isomorphism acts as follows. It takes each pair, A lambda in the direct sum, to, well, the obvious candidate is A plus lambda 1 plus, which is indeed obviously a vector space isomorphism. But this is not an algebra isomorphism. And if we want to get an algebra isomorphism, we must do the following. So this map is easily seen to be a unital algebra isomorphism. If we now combine 1 and 2, we conclude that if A is a unital algebra, then for each element in A, the non-unital spectrum of A is the usual spectrum and 0. So in other words, 0 is this point, 0, the origin, is the only possible point which is in the non-unital spectrum, but which is maybe is not in the spectrum. Sometimes it is in the spectrum, and in these cases, these two spectra are the same. In other cases, it is not in the spectrum, but this is the only distinction between these two spectra. Okay, now by using this, we can extend the notion of spectral radius to the non-unital case. So we give the following definition. If A is a Banach algebra, not necessarily unital, and little a is an element in our algebra, when we define the spectral radius of A by the following formula. Here lambda runs over the non-unital spectrum of A. So we see that it follows from part 3 of the previous exercise that if A is already unital, then this notion, this new definition is consistent with our previous definition, where we take the supremum over the spectrum of A, because the only distinction is 0, and of course this, this point doesn't affect the supremum. And now, since the unitization of A is also a Banach algebra, and A is isometrically embedded into its unitization, we get the non-unital version of the Berlin-Gelfand formula. Which is exactly the same as in the unital case. So this is immediate from the fact that unitization is also a Banach algebra with the same norm. So in other words, not the same norm, of course, but the norm which extends the norm of A. And so we simply embed in A into A plus and calculate the spectral radius in the unitization by using the Unitized Gelfand formula. Okay, now we are ready to extend the notions of maximal spectrum and the Gelfand transform to the non-unital case. Maximal spectrum and Gelfand transform for non-unital Banach algebras. So we suppose that A is a commutative algebra, not necessarily unital. It turns out that in this case, the set of all maximal ideals is no longer relevant. It is useful to consider only those maximal ideals which have the following property. So we give the following definition. We say that an ideal in A, I in A, is modular. Some people say regular. If the quotient of A modulo I is unital. So explicitly, this means that there is an element U in I in A such that A minus AU is always in I for each A in A. So this is just the this is just any representative of the identity in A modulo I. Such an element is sometimes called a modular identity. And it is easily seen to be unique modulo I. So any two modular identities can differ only by an element of the ideal. Well, let's look at some examples. First of all, it's clear from the definition that the zero ideal is modular if and only if A is unital. And actually, in this case, all ideals are modular. The second example, or rather an observation, is that if chi is a character of A, then the kernel of chi is always a modular ideal. Well, indeed, if chi is zero, then this is obviously true because the kernel is A itself. And the zero algebra is unital, by the way, by the very definition. And if chi is non-zero, then, then in this case, the kernel has codimension 1. So a module of the kernel is isomorphic to the complex plane, which is unital. So the kernel is always the kernel of a character is always a modular ideal. And here's a counterexample. Let A squared denote the linear span of all products AB, where A and B run over the algebra. So if the algebra is such that A squared is strictly smaller than A, and if you take any vector subspace, each vector subspace I, such that A squared is contained in I, and I is properly contained in A, is a non-modular ideal. Well, indeed, it is an ideal because it contains A squared. And it is not modular because essentially for the same reason. If we take the quotient of A modulo I, then the product on the quotient will be identically zero. So the quotient is a non-unital algebra. The algebra is not zero, but the multiplication is zero. So such an algebra is not unital. And here's a concrete example. For example, we can take the algebra of polynomials with zero constant term. This is our algebra. And I is TA. So this is a concrete special case of this general situation. This ideal is not modular in A. Well, modular ideals have a number of advantages. For example, we have the following result. Theorem. Each proper modular ideal of A is contained in a maximal modular ideal. The proof is a simple exercise. So if we look at the proof of the unital case, it's easily seen that it extends to the non-unital case, provided that we consider only modular ideals. If we speak about arbitrary ideals in A, then this theorem fails. So there are some examples of ideals, non-modular ideals, which are not contained in any maximal ideal. So the word modular here is essential. Okay, now let's introduce some notation. First of all, we define the maximal spectrum in the non-unital case. The maximal spectrum of A is by definition the set of all maximal modular ideals of A. And as before, we introduce the character space. The character space of A is defined as before. So this is the set I had, which consists of all non-zero characters. For some technical reasons, it will be convenient to enlarge these sets a little bit. So we introduce some more notation. So we define the set A hat plus. So this is the union of A hat and 0, where 0 is the 0 character. In other words, this is the set of all characters of A, including 0. And we define the set max plus of A as the union of the maximal spectrum and A itself. So A itself is also an ideal in A for trivial reasons. And we add it explicitly to the maximal spectrum. Okay, now we have the following proposition. So we have the following commutative diagram. Of the following form. So we can take the maximal spectrum of A plus and construct map from this maximal spectrum to max plus of A, which is defined as follows. It takes each maximal ideal of the unitization to its intersection with A. And I claim that the result will be either A itself or a maximal ideal or a maximal modular ideal of A. Similarly, we have a map from the character space of the unitization, A plus hat, to well, in our notation, this is A hat plus. I mean, to the set which is defined here is the set of all characters of A. And this arrow takes each character of A plus to its restriction to A. Clearly, this is a character, maybe 0. And finally, we have 2 vertical arrows from here to here, which take each character to its kernel. Let's denote this diagram by D. Well, I claim that the diagram is commutative, and the horizontal arrows are bijections. And the horizontal arrows are bijections. The proof is an exercise for you. In fact, well, the lower horizontal arrow is a bijection by the universal property of the unitization. This is trivial. So the only non-trivial point is to show that the upper horizontal arrow is a bijection. Fortunately, if A is a Banach algebra, then the upper horizontal arrow is a bijection for some very simple reasons. Namely, we have the following proposition. Suppose now that A is a commutative Banach algebra. Then, first I claim that all maximal modular ideals of A are closed. And second, that all arrows in the above diagram are bijections. Well, again, the proof is an exercise for you. I'll only explain why it is true. The proof of the first part is almost identical to the proof in the unital case. So at the previous lecture, we proved that all maximal ideals of a unital Banach algebra are closed. So the same argument, exactly the same argument, shows that all maximal modular ideals of any commutative Banach algebra are closed. And now, again, the same argument as in the unital case shows that the correspondence between A hat and max of A is a bijection. So after we add only one point here and here, we still get a bijection. And now we get a trivial proof that the upper horizontal arrow is a bijection because the diagram is commutative. The lower horizontal arrow is a bijection, and the vertical arrows are also bijections. So obviously this implies that the upper horizontal arrow is a bijection. Okay, we can now topologize our spaces. We define the Gelfand topology. The Gelfand topology on max of A, which is identified with a hat, and on max plus of A, which is identified with a hat plus to be the restriction of the weak star topology. On A star. So the definition is the same as in the Unital case. But here we have two sets, the set of all maximal modular ideals and the set of all maximal modular ideals together with one new point, the algebra A itself. And respectively, we have the set of all non-zero characters, A hat, and the set of all characters, including zero, A hat plus. We have the following proposition. All these spaces are Hausdorff. Max A and max plus of A are Hausdorff. Max plus of A is compact. And is homomorphic to the maximal spectrum of A plus. So in other words, the this bijection in this diagram becomes a homeomorphism with respect to the Gelfand topology. The maximal spectrum itself is locally compact, but is not necessarily compact. Max of A is locally compact. And finally, max plus of A is the one-point compactification of max of A. Well, why is it true? Again, the set max plus of A is identified with a set of all characters, including zero. Is a set, and the set of all characters is easily seen to be closed in the unit ball of A star with respect to a weak star topology. So the same argument as in the Unital case shows that this set A hat plus is compact. And the remaining statements is pure general topology. So we have a compact space, max plus of A, we remove only one point, and we get a locally compact Hausdorff space, which is not necessarily compact. So in general, we cannot prove, and this is not true, that the maximal spectrum is closed in max plus of A. It will be closed only if the zero character is an isolated point. Okay. So now we can define the Gelfand transform. Oh, sorry. Okay. First of all, the Gelfand transform of an element in A. The Gelfand transform of an element little a in A is defined in exactly the same way as in the Unital case. So this is a function A hat on the maximal spectrum given by the following formula, where we interpret chi as a character array. So what can you say about this function? We have the following proposition. A hat is continuous and vanishes at infinity. The proof is very easy. By construction, A hat, well, the continuity of A hat is again proved in exactly the same way as in the Unitital case. Continuity is clear. See the Unitital case. And if we take the one-point compactification, this is nothing but the this identified with the zero character. And of course, by construction, A hat vanishes at this point. So it vanishes at infinity. And we have already seen that if you have a compact Hausdorff space, sorry, if you have a locally compact Hausdorff space and a function on its one-point compactification, which vanishes at the infinite point, then the restriction of this function to our space vanishes at infinity in the sense of our original definition. This implies that A hat vanishes at infinity. Okay, and finally, we introduce the Confined Transform of our algebra. The Confined Transform of A is a map gamma from A to the algebra of continuous vanishing at infinity functions on the maximal spectrum, which takes each element little a to the function little a hat. So we see that the definition is exactly the same as in the Unitital case, but now we know that this map acts not just to the algebra of continuous functions, which is not a Banach algebra, because now the maximal spectrum is not compact, but to the algebra C0, which is always a Banach algebra. So if we look at this definition, we see that we get the following commutative diagram, which relates the Confined Transform of A with the Confined Transform of its unitization. So this is the Confined Transform of A. A is contained in its unitization. So here we have the Confined Transform of the unitization. But we already know that the maximal spectrum of the unitization is identified with max plus of A, which is the one-point compactification of the maximal spectrum of A. And C0 on the maximal spectrum becomes an ideal in here. And this diagram is commutative by construction, by the very construction of the Confined Transform. And this diagram really implies the basic properties of the non-unital Confined Transform. So we have the following theorem. Suppose that A is a commutative Banach algebra. Then, first of all, the Confined Transform of A is an algebra homomorphism. Second, it is continuous, and the norm of gamma is less than or equal to 1. So let's recall that in the unital case, it is exactly 1, but in the non-unital case, it can be strictly smaller than 1, strictly smaller than 1. Property 3, the norm of the Confined Transform of any element, supremum norm, equals the spectral radius. So this is exactly as in the unital case. Property 4, the non-unital spectrum of little a is almost the range of the respective Confined Transform. The only possible distinction is 0. So 0 is always in the non-unital spectrum, but it's not necessarily in the range. But if we add 0, then we get an equality. And finally, property 5. Property 5. The kernel of the Confined Transform is again the intersection of all maximal ideals A, which is the same as in the set of all quasi-nilpotents in A. Okay, so these are the basic properties of the non-unital Confined Transform, and all of them are more or less immediate from the above diagram. So we know the properties of the Confined Transform of A plus, and since the Confined Transform of A is essentially the restriction of the Confined Transform of A plus to A, we see that gamma satisfies all these conditions. Okay, so that's all I wanted to tell you today. And the next lecture, we begin to discuss C-star algebras. And in particular, we will prove one of the most fundamental results, the so-called commutative Gelfand-Naimark theorem, which states that if A is a unital C-star, a commutative unital C-star algebra, then its Gelfand transform is always an isometric isomorphism. Okay, thank you.